Hello, hello. Who do we have here? There is Raymond, and there is Lila, and there is, wait a minute, and there's Joyce. Okay, and there is Shen. Hello, 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 and yes, and here's the chat. Hold on. Good afternoon, Camille. Wait, how'd that just happen? Oh, sorry. Good afternoon, Danielle. Good afternoon, Tania. Good afternoon, Camille. Good afternoon, Luis. Whoa. Oh my God. Okay, that's hilarious. That is totally a portal, Shen. That should, I mean, that already goes in like 4 different portals for points, but I should make up a new portal just for that. That is awesome. Why have I never seen that before? Okay, that's hilarious. That's of course how about, when you wake up during class and you find out you're supposed to be teaching physics. But okay, yes, that's awesome. Good afternoon, Abdul. Good afternoon, Leah. Hello and good afternoon, Mantra. Oh, more people, sorry. Okay. Good afternoon, Samaya. Good afternoon, Michael. Awesome, awesome. Who else do we? Oh, and Michael. Yes, Michael in both. Right, in both. Okay. Awesome, awesome. And Nico is coming. Okay. Good afternoon, Gerasimo. Wait, I know you told me this. I think I say Jerry. No, tell me again. I think I say Jerry, you said? Well, you'll tell me. Yeah, that's right. Okay, cool, cool, cool. Awesome. Thank you. All right. Um, da da da. Okay, more people coming. Okay. Okay. All right, so we're going to continue. Oh, this is fascinating. Hang on a second. I'm sorry. Oh, that's hello. Yes, hello, Nico. Wait, what am I doing? Oh, I am messing up. All right, we're going to continue going over, like we said, we're going to continue with homework 1, which takes a while. We're going to continue, we're going to be talking about question 4. We got an answer to question 4. I'm aware of that, but now we're going to start. Well, I'm going to go to question 5 and get an answer there too, so you can see if you're doing it right or whatever. And then we're going to back up and expand on many of the concepts that are necessary for solving question 4 and 5. Um, uh, so the plan for today, well, is to get to this, which we started yesterday. Like, what my goal is to try. So the way that we're getting the answers to question 4 and 5 on homework 1B, thinking on a spring, the way that we're getting answers is by applying the principle of mechanical energy conservation. That's what I'm doing, and that's the math that I'm doing. When I finish doing question 5, I'm going to back up and start trying to expand on where these concepts are coming from or why they are true or how they work. Specifically, I want to re-expand on what it means to say that the work done on a system transfers kinetic energy to that system. I want to expand on what that means and specifically like the calculus implications of it. Well, we'll get to that. And then I want to expand on, or maybe say for the first time to many people, what it means to be a conservative force and how the notion of conservative force facilitates the concept of potential energy. I mean, so that's a goal. And we may actually not get to all of that today, but that's the goal. It just reminded me there was one other bookkeeping item. Well, I mean, look, secretly, really, what's about to start happening with question 4 and 5, if nothing else, what this is really about the next couple of classes is I really want to start making sure that we actually understand what an integral is from calculus. Like what an integral from calculus really is, why we use it in physics. In other words, how to know when to use it and how to set it up. That's really what's going on here for the next couple of classes. It's about the nature of the integral from calculus. That's really the point. I keep feeling there was something else I was going to say, but also let me just see. Um, again, if there's any questions at all about any what we did yesterday, please stop me before I start, or well, please stop me at any time. But I'm happy to answer any questions from yesterday. Also, a couple of bookkeeping items. You still can turn in drafts and uploads and revisions on homework 1B. I hope that, oh, yes, okay. I hope that's clear. There's still time for anybody and everybody to get all the points on homework 1B. If you haven't turned it in at all, I mean, it's the first homework of the year, so I'll still be largely forgiving about that right now. I mean, soon we're going to get to a point where in order to be able to get all the points on homework, even if it takes you infinite revisions and even if it takes you lots of uploads, which is fine, which is maybe even good, we're going to get to a point soon where in order to be in that position, you have to at least turn in the first draft on time, the day it's due, and then you can get all the points. I think right now, still with homework 1B though, we're being forgiving, so just do it if you haven't done it. And homework 1A, I've not forgotten about. We will go back and go over homework 1A. I think I already mentioned, I think it's the case that if you handed in on time and you did anything reasonable at all, I think you got all the points for that. But I will show you why we did that in like a day or maybe two. Okay, I'm just, oh. Okay, I'm just looking at the chat. Okay, sorry, I did not. So I'm a little bit. If any emails came in, I am usually pretty good about emails, but if emails came into me today, I mean, I teach all day on Wednesdays, so if there was an email today, I didn't see it. And I apologize, but I'm glad to hear if people are feeling. I mean, great. Great. Okay, someone's coming in and out. Okay. So there was one other bookkeeping. Oh, one other quick bookkeeping item. With a couple of you in this section, in this class, there seems to be a little bit of a thing that seems to be happening. Well, now, and I'm about to make an announcement. One person absolutely has already corrected this, what I'm about to say. So I know that. So this is a strangely timed request, but it seems to be happening from time to time that sometimes some of you, like I can give you, if you're getting comments on your work from me, but you're not actually getting the work back at all, like the document back or something like that, or something seems to be missing, or you're getting a grade, but not, make sure that you have room in your Google Drive. Like I think with at least two students in this class, there was an issue where like the exchange couldn't happen anymore because you had run out of room in your storage space in your Google Drive. So when in doubt, if ever you're hitting a glitch or you think you're missing things from me that everybody else is getting or something, check that. I think, again, with one person that was an issue, and I think that person just fixed it recently, so thank you. But it seems to be happening, so just always check that. Okay, I think, oh, okay, cool. Okay, so we're going to start. So I'm going back to, if there's no questions, I'm just making sure if there's no questions or concerns, we're we're going to go back. We're going to go to homework 2. I'm sorry, homework 1B, and I'm going to just go straight to homework to problem 5 before doing any expansions or anything. And of course, this. Okay. There's something, sorry, there's something very off today about. Okay, so I'm just repeating. So question five. Question five is, well, question five is when the instantaneous speed of this object is 3 meters per second, what position is it at? Right? So no, this is the same as question four, only it's in reverse direction. The question four was at a given spot, what is the speed? This question is given a given speed, what's the spot? Right? It's really the same question. It's just here we're giving the speed and we're asking for the spot. So the first thing I want to say is indeed the GDP here, the truth that that we need to employ for this problem is the same as the general truth for the last question. And I think that most of you, when you did the homework, realized that it is an energy conservation question again. Well, let me say again, like I said on Monday, anytime we're looking at a speed to spot correspondence, you know the speed at one spot, you want to know the speed at another spot, or you know the spot at one speed, you want to know the spot at another speed. That always calls for energy conservation. Conservation, of course, means same value throughout. But one little nuance that I'm trying to get across to you that sort of never occurred to me until it occurred to me is that, I mean, there's different types of conservation in physics and in science. I mean, there's energy conservation, there's linear momentum conservation, there's angular momentum conservation. For example, um, whenever we're thinking the reason to use energy conservation ever, the time that we would ever choose to use energy conservation is when a system is moving, when a speed is changing from spot to spot. That is very specifically what I'm saying is to conserve energy is to maintain the same value of energy at all places, as opposed to other kinds of things like such as linear momentum. When we conserve linear momentum, like in a collision, we maintain the same amount of momentum at all times. It's fundamentally different. And I, I'll So I'll move on. But the real reason I'm saying that energy applies to space and momentum applies to time is that that's kind of a signal of when to decide to use energy conservation. If the whole analysis of the problem has to do with something varying from space to space, as opposed to time to time, that's when you use energy. Okay, so we're going to use the same concept as we use in question 3. However, and I think a lot of people knew that. However, now we have to really, this is where GDP step 3 really becomes important. We have to be clear in our mind what the GDP is. The GDP is that all the amount of energy at one spot is the same as all the amount of mechanical energy at another spot. The way to write that mathematically is only this way. Well, like in other words, the energy at one spot, the total mechanical energy at one spot equals the total amount of mechanical energy at another spot. What is total mechanical energy? It is all of the kinetic energy plus all of the potential energy at one spot has to be the same as all the kinetic energy plus all the potential energy at another spot. In right. That's the GDP. A really long way of saying we're not saying kinetic equals potential. We're saying kinetic plus potential over here equals kinetic plus potential over there. That is the universal truth. Now, if we start applying to this particular problem, in this particular problem, how is this driving me crazy? What I'm trying to say, you might want to say in your notes, because sorry, I'm having issues with the. So kinetic energy is always 1f squared in classical physics. I mean, in all of physics 203 and all of physics 204, kinetic energy is always 1f squared. Potential energy is the more complicated thing that we have to talk more and more about today's class, next class. But in this case of a spring potential energy is 1f squared. Okay, so this still looks exactly like what we did for question 4. Well, in this case, like in all cases, what are X1 and X2? They're the two different spots that we're comparing. What two spots? One spot where we know the speed, or when we know all the information we're solving for, and the other where we're solving for the information. So the spot where we're solving for is called X. Like we're literally looking for the X for which V is 3. The spot that we know something about already, the truth is there's more than one, but one spot that we already know about is the equilibrium position, 0. Or you could say that we are, like, because we know at the equilibrium position, the speed is 3.87. Or you could say that we already know that at the 15 centimeter, the initial position, we already know that the speed is 0. Either one is a known position. What we're solving for is the position X, where that's what we're solving for. So we know that at X equals 0, X equals 0, right? So that term goes away. So that's a nice helpful cancellation. But notice, but that's the only term that cancels. This is where a lot of people made a mistake. Like 1f squared, like right, we're solving for the X at which V equals 3. So V equals 3, not 0. And X equals X, not 0. So there's nothing on the left side that crosses out. There is something on the right side that cancels out. The reason I'm making a big point about this is you notice we're not saying like what. So basically, to be blunt, what a lot of people did for question 4 is they said 1f mv squared equals 1f kx squared, and they solved for v, and they got it right. Now I don't think And then they did the same, and they understood that the two problems were very similar. So they did 1f mv squared equals 1f kx squared for this, but then got it wrong. What I'm trying to tell you is the two problems are very similar. They do use the same step 3 GDP, but the step 3 GDP is not, and never should be, 1f mv squared equals 1f kx squared. That's not a truth. That's not a thing. Like, what's not a thing? I'm saying writing down 1f mv squared equals 1f kx squared, or put another way, writing down ever potential energy equals kinetic energy, that's a thing that a lot of people do, but it's not a thing that anybody should do. There's no that doesn't make any logical sense. The only time that the potential energy of something should equal the kinetic energy is when the thing happens to be right in the middle of its journey. That's not what we're looking at here. In general, what is true is that the sum of kinetic plus potential over here equals the sum of kinetic plus potential over there. So, long story short, I mean, again, this is kind of like the difference between a triple equal sign and a double equal sign. In the last problem, we started off with 1 of mv squared plus 1 of kx squared over here equals 1 of mv squared plus 1 of kx squared over there. We started with that. Then we started doing crossouts, and two of the terms crossed out because we were looking at very special spots. We were looking at spots where two spots, one where x was equal to 0 and one where v was equal to 0. So we got a crossout on each side of the equation. So it ended up being this nice thing, looking like this nice thing. 1f mv squared equals 1f kx squared, right? But don't memorize that. That is a PAW. It's not a GDP, if that makes sense. Like it's a double equal sign, not a triple equal sign. It just sort of emerged that way for that particular situation. The GDP here is that, I mean, I think you get my point, but the thing that is true in both cases is the sum of all the energies over here equals the sum of all the energies over there. So then I could cross out one of these terms, but not all of them. So that, okay, so that's gone, but then I can still factor out a 1/2. So out of all the terms, so the 1/2s go away. So now I have mv squared plus kx squared, the x that I'm solving for, equals the mv squared at x equals 0. Like that's what I have so far. I know there's somebody in the waiting room. I'll get them in 1 second. Sorry. Okay. Okay. And so notice again, I'm postponing numbers to the last possible minute. I mean, like, I'm like not putting in the numbers until the last step. Notice also now, this is another mistake some people make, not a lot, but people tend to make this mistake. Notice here, now I have like, okay, two things. I have mv squared plus kx squared equals mv squared. First of all, it might look like I have mv squared on both sides. Can't I cross it out or something like that? It's not the same mv squared. Oh. Yeah. It's not the same mv squared. It's in particular, it's not the same v, right? This one is v equals 3. This one is v equals 3.87. Where did I get 3.87 from? From the problem yesterday. So you can't cross out the mv squareds. The other thing is, can you divide both sides by m? No, because there isn't an m in all, like, because I can't factor out an m, right? You cannot cancel out the m's here. There would have to be an m in the kx squared term to cancel it out. So what do I do? Well, I remember, what is it that I'm solving for? I'm solving for v. So I get the v that I'm solving for. Sorry. I'm solving for x. I'm solving for x when the v is 3. So I get the x term by itself. So I'm looking for x. Oh, sorry. Okay, 1 second. I know there's someone in the waiting room. I thought there was something. Wait a minute, is there not? Okay. Um, okay. So, and this is starting to look thick to some of us, maybe, but it'll get more and more simplified. Again, for a lot of reasons, the trick here is just postpone the numbers for as long as possible. Get used to doing the algebra or the trigonometry or the calculus. Um, right. So now this is all just, I mean, it looks annoying, but it's all just stuff you could do on your calculator. There's no, they're all just numbers. So I think when you're done here, you get, okay. Oh, wait. Oh, sorry. There is somebody. Wait, I thought I saw someone in the waiting room. Wait, is there someone in the waiting room? One sec. Do you mind? Okay. Sorry. Yeah, I thought I saw that and then I went to, okay. So, okay. Um, hang on. So that's the answer to that one. I'm going to pause for a second, partly because I got look at that for a second and see if you have any. So basically, that's the correct answer. Like if you put 0.096 or 0.094, that's a rounding thing. I mean, I'm chopping off digits. That's fine. But the answer is not 0.113 or 0.116 or something. If you got something like that, if you got like 0.11 something, I think that's not rounding. That's you believing that 1/2 mv squared equals 1/2 kx squared, which I'm saying is not the way to do this. So think about that for a second. Just see if you have any questions. I'm stepping out for 1 second. Okay. Oh, go back to the first. Yes. Would I be able to go back to the first slide? Oh, sure. Sure. Wait. The like literally the first anywhere you want, but do you mean literally the first? Like, hold on. Like this? Tell me. Is that when you? Yeah. Okay. Great. Okay. Oh, great. Thank you. And of course, to everybody, not he gets points for that, right? Like he should submit. Yes, he should submit to please go back portal and get points. Like it's a good thing to do that. Really, if nothing else, it just tells me that somebody's paying attention to something, right? Okay, but which people clearly are. Like, for example, definitely Lila, just saying, and definitely Raymond, and definitely Joyce, just saying. Okay. All right. Now, all right. We're now that I've done that, well, yeah, I want to back up a little. So this is now me. So if you were looking for what to do for the homework, essentially that. I mean, could you get all the points if you did what we just did? Yeah, basically. Yeah. But now I want to back, but now what I feel is I want to back up and really show you where some of those things came from, because where they came from, we need for the rest of the semester and we would need for exams and things like that. So This is like now notes. I mean, we're not done with the homework. Don't get me wrong. I know there's more questions on the homework. In fact, yeah, in fact, sorry, I know I'm a little bit not in perfect condition today, but I mean, as though I ever am, but uh um I just changed my mind. Pardon me for a second. I think we'll just answer the rest of the questions until the last one. I think we can answer 6 and 7 and 8, just so that we're all on the same page, because they don't take very long to talk about, I don't think. And then I want to go back and expand on this. So bear with me for a second. So now, okay. So, oh, oh, yeah, wait, great question. Yes, we are. Well, we're going to start. So okay. So Lila's asking a great question. A, and the question is, will we go over question 9 next time? A, definitely we are not going over it this time. Correct. Like we're not even pretending or dreaming of getting to question 9 today, for good or for bad. I apologize, but that's the case. I mean, and that's always the case. Now, as far as next time, probably it will be next time, but I will admit, question 9 is the point of this whole thing. Question 9 is hard. It's big. If you're at all eager or anxious to see it, good, you're in the right place. Like all of this is supposed to be a build up to question 9. It's all about question 9 in the end. So a couple of things about question 9 is, first of all, even when I start it, I know this is going to sound annoying, but even the day I start it, we may not even finish the whole thing in one class period. I mean, I'll get you an answer. You'll get an answer. In fact, I think I can tell you the answer right now. I think the answer is 0.116 meters. Um, well, I'll get to an answer, but there's a lot. But question 9 involves new calculus, new physics. It's sort of like what kicks off this physics 204 real stuff. Technically, until question 9, everything is kind of reviewish from physics 203. So once I start question 9, you're going to all have to bear with me, please, because that's when we unpack all the new material. So it might not even be finished in one day. As to whether it will be started next time, I think so. I hope so. I think so. I hope so. Um, but in the middle of all that question, because it's the kickoff to everything else, honestly, somewhere in there is where we go over homework 1A, which seems like it has nothing to do with anything. I know. Homework 1A seems like it has nothing to do with anything, but it actually does set the stage for like why I'm bothering. Why am I spending all this time on a mass on a spring going back and forth? And how does this have to do with physics 204, blah, blah, blah. So basically, long answer short, long answer short, I mean, short answer long. We will not get until question 9 until at least next time. One way or another, it's going to take a couple of the next upcoming classes to do, for good or for bad, but we definitely will do it. If that's your concern, we're not moving on to homework 2 or anything else until we fully unpack question 9. If that's the issue, that's definitely maybe privately tell me whether I answered that question at all or whether that was too much or too little, especially since I kind of see you a lot during the week. Let me know in private whether that was too much or too little on that question, but because I'm overinterpreting what your concern is probably. But anyway, good question though. Oh, okay. Yeah, definitely. It's some, yes, yes, I promise. Yes, but sorry to take so long to get there. Noted. All right. So to that spirit, I'll quickly go over questions 6, 7, 8 right now. Maybe I'll even more quickly than because they just starting to bore me too. All right. So, I'm just going to say, so question 6, and these are just answers, right? Question 6. All right, these are just answers. Stop me if you have any issue with it. But I think question 6, like, how far is this thing going to go on the other side until it turns around again? The answer is the same distance on the other side as it started with on the first side, 15 centimeters, right? Hopefully that's just intuitive to you. Hopefully you just, sort of just feel like that seems right. And you're right. But here's the thing, rigorously, the reason that's right, the reason it'll go to this why it'll be symmetric is because we believe that this thing is conserving energy. To say that it's going to go to the other side is to say physically, this thing is not going to lose energy. Mathematically, whatever amount of potential it has when it starts will be converted fully to kinetic when it gets to the equilibrium and converted fully back to the same amount of potential by the time it gets to the other side. So mathematically, the 1/2 kx squared on the other side had better equal the 1/2 kx squared on the original side. And the only way the 2x squareds are going to be equal is if one x is positive 15 and the other one is negative 15. So you could show it literally by, again, using the same GDP as we used in the last problem. So the answer is negative 15. I'm going to just keep going on. I'm going back and forth between screens, but if you have a question, definitely ask. But other than that, I'm going to say that the same reasoning for question 7. If this thing is truly conserving energy, then it's going to keep landing on the same displacement each time. So then there's no reason for it to ever get shorter and shorter. So it's going to keep on going forever. You might say, is that really realistic? Well, it's as realistic as believing energy is conserved. Like, of course, the better the spring is, the more realistic this will be. The longer the spring is, the more uniformly tight the spring is, the more close to this ideal the whole thing will enact. If you want to say, I don't believe it's going to be perfectly infinity, or I'm not going to believe it's going to be perfectly negative 0.15, I agree with you there. Not in the laboratory, it won't be perfectly, but I'll tell you this. If it's not perfectly 0.15 negative or perfectly infinity, then I don't know what number to write down. Like if there's any number that means anything, it's those. And more to the point, if you're going to reject negative 0.15 or you're going to reject infinity on the basis that those numbers are ideal, then you'd have to reject every answer that we've gotten to so far, like the 0.095 and the 3.87. Just a quick way of saying, don't be fooled. Don't do the CUNY thing. Don't think don't think that just because the 3.87 is more precise looking than the 0.15 or the infinity, don't be fooled into thinking that the 3.87, because it's more precise looking, that it's somehow more realistically true. It's exactly as or as not realistically true, like the 3.87 answer, as these two answers right here. They all assume energy conservation. They assume that friction is playing a low role in the situation. Does that ever perfectly exactly happen? No. But last point on this, you could certainly construct springs. You can certainly construct springs or observe springs in a laboratory where they're long enough and tight enough that the friction makes a low enough difference that any instruments you use to make any measurements on the original spring or the original motions, whatever level of precision you would set the instruments to make all these original numbers that the problem began with, that those instruments would not be able to pick up any deviations from these final answers. That's a mouthful. What I'm really saying, though, is, well, it's a discussion for another day, I guess. But I'm just saying, in the end, ideal situations in physics are not ideal like fantasy, like fake, like Smurf Village, like only in my mind. Ideal means that we're in physics, not in math. We're in physics. So we're in science. So ultimately, everything we get to believe in is what we see on measuring equipment. It's all about data in the end. So it's absolutely conceivable. So when we say something is ideal, we just mean that the deviations from ideal are too small to pick up on our measuring equipment. And if we can't pick them up on our measuring equipment, we have no basis for believing in them or using them or quantifying them. So ideal really does exist in the physical world. Like it's not a fantasy. Anyway, I'll move on. So that's 6 and 7. Sorry. Then 8. Okay, so just do 8 now, and then we'll go back to question 8. Sorry. Question 8. Yeah, I guess I'll just say the answers again. Question 8. Okay, I'm going to start with this. From the edge to the center, the magnitude of the velocity, i.e. the speed, goes up. How do I know? Because the speed at the beginning is 0 and the speed at the center at the equilibrium is 3.87. So the thing is, so I let the thing go from rest and it's going faster and faster as it goes into the center. So its speed is going up, as you might expect. Its speed is going up, so it is accelerating. Its speed is going Its speed is going up, so it is accelerating. It has acceleration. But notice this, its acceleration from here to there is going down. This is now, again, where physics starts to get confusing to people sometimes. I think it's where physics starts to become physics and starts to become interesting. But, you got to keep velocity and acceleration straight. It's almost like the big point of physics 203. We say that this object is accelerating. That doesn't mean its acceleration is increasing. It doesn't mean that it's accelerating at greater and greater rates. In fact, the opposite. This thing is getting fast as it comes in from the edge to the center. It's moving faster and faster. It's gaining speed, but the rate at which it's gaining speed is, in fact, declining, right? It's getting faster and faster by smaller and smaller increments, by slower and slower rates. If you, and I do, that's hugely important. I don't think it's obvious. I just think it's hugely important. How do I know? How do I know? Well, for one thing, F equals negative KX and F net equals NA. Like we look at your answers for question 1 and 2 or whatever, or 3 and 4, 2 and 3. Right at the edge, when it started, it had no speed whatsoever. It wasn't moving. But from the moment we let it go, even though it wasn't moving at all, it was already accelerating at an enormous rate of, I believe we calculated an enormous rate of 100 meters per second squared. Right now, there's a negative sign on that, but that just meant it's accelerating toward the left. Don't let that fool you. That doesn't mean it. The negative sign does not mean it's slowing down. At that moment, it's speeding up at a rate of 100 meters per second squared, i.e., if it were to continue this trend forever, then every second it would gain 100 meters per second of speed. So it's good, right? But the confusing thing, and why? Because it's being pulled so hard by the spring at the. Sorry, I'm running out of batteries. Oh yeah, this is. I may have to stop for a second and get a charger, but bear with me. Well, I will stop in a minute and get a charger, but I'm just, for the moment, I'm just saying right at the beginning, even though this thing is not moving at all, it's accelerating at a high rate. If that confuses you, I'm going to say it again. It's not moving at all at the beginning, but it's accelerating at an enormous rate. If that confuses you at all, or even slightly, or if it doesn't confuse you, but you're like, I get it, but like if you have any kind of bump in your brain and all that, you know what that means? You know what that means? It means you're being honest with yourself and with me, or with me. Like, welcome to physics. Like, don't. I mean, I'm not wanting to confuse you. If you're solid on that, if you get it, good. Like, I mean, so do I. But we should recognize that's a tricky aspect of physics, and it gets a little. And how do I know? Because the spring is yanking on it so hard at that point. The spring's like, come on. And acceleration is that. Acceleration is like how you're going to change your motion, not your motion, how you're going to change your motion. So the spring is like, come on. So it's like ready to, it's like the accelerometer is high. Now it starts moving in. The spring is pulling it in. But as it comes in, the spring is getting more and more relaxed. This is the nature of springs. As it's coming in toward equilibrium, the spring is getting more relaxed. So it's getting faster and faster. The object is moving faster and faster. By the time it gets to equilibrium, it doesn't stop. It's got enormous amount of motion. It's ready to keep on going. It will keep on going. It's going really fast, 3.87 meters per second. I mean, that's not like literally fast, but like a lot faster than before. 3.87 meters per second. However, at this moment that it's booking so hard in that leftward direction, it's got no acceleration whatsoever, right? The spring is now perfectly relaxed. The spring has the mass where it wants the mass to be. The mass is going to keep going, but the spring is not doing anything to it anymore. It's not pulling it anywhere. There's no F net on it anymore. So right now the spring has zero acceleration. I mean, like we said on Monday, right? So please make sure if you find this a little bit janky at all, like even like you basically get it, but part of you doesn't, you're probably in the right intellectual zone. If you literally think that everything I'm saying is completely obvious and always was, and there's like nothing even to see here, Maud, or whatever, that's an expression. Like if you're just like, what is the bit? Then I don't know. Like you're either like way on top of things, or maybe you're kidding yourself slightly. I'm just saying, and we're going to move on. I'm going to charge the computer, but I'm saying, right, and I'm not done. And and it basically means, so Lila, we're going to get to question 9, like in November. Is that okay? No, okay. No, we won't. But so I'm dragging this out a little bit, but I want to be clear. Velocity is not the same as acceleration. We're going to enter a big calculus zone here in a minute with integrals and every. So if nothing else, I'm saying like, please, somewhere in your mind, be straight that the second derivative is the derivative of the first derivative. Like acceleration is a derivative, velocity is a derivative as well, but they're different derivatives. They don't have to track the same way at the same time. So the velocity is going up, the acceleration is going down. I have to finish this problem, but I have to get a plug before I lose you all. Hold on one second. Sorry. Okay. All right. So that's that. But then now, as I said, we're starting to get into calculus here. Then the real question is, what about the next thing? Like we never talked about that in physics 203, or maybe in calculus. Like the next thing is, what about the third derivative? Like, so in other words, this is dx dt, right? This is d2x d. And again, I'm not doing the 5-step method right now. I'm just talking. Oh, clearly, I'm just talking. So the first derivative is going up in this quadrant, and the second derivative is going down. But now it's asking, what about the third derivative? Good question. I've never thought about that before. Well, I'm not sure. I mean, I am sure, but I mean, I'm not sure how to go about this. What should I do? Well, maybe one thing I can do is look for a pattern. Maybe let me step back. Like, sorry, that's supposed to be a T. Okay. It, what is going I, I wrote down an answer about the first derivative of a function. I wrote an answer about the second derivative of a function. Now it's asking me about the third derivative of a function. I don't know what to do. So it'd be nice if maybe I had some pattern to base my work off. So why don't I ask myself, what about original function? Now I'm not saying this is, in other words, wait, what's happening to X? when it comes in from here to here? Well, just very concretely, like it's such a simple question. It's almost sounds harder than it is. Like when it's coming in from x equals 0.15 to x equals 0, x is going down, right? Remember, we're not worrying about negative signs. We're just talking about magnitudes. The magnitude of x is going down from 0.15 to 0. So x is going down. Now, why did I just bring that up? Like the question didn't ask me that. I'm thinking that because I'm looking for a pattern. So let me read. In other words, i.e. So if I look at this pattern that seems to be establishing itself, it would seem based on no other reasoning that D3x dt3 seems like probably is going up just based on this pattern. Is that a proof? No, but it's a pretty strong suggestion that, right, like that what's so-called the jerk, the rate at which the acceleration here is changing seems like it's going up. Also, if you notice, wait, is this worth saying? Let me just think for a second. Actually, yes, for the moment, I'm just going to leave it at that. I mean, there's other ways to argue and verify this, but I think if you look at the pattern alone, that's what's going on. Yeah, I think I'm just going to leave it at that for the moment. I mean, certainly you could still put questions in the chat, but I think that's the answer. Actually, let me take a breath for a second to think if there's a better way I can say that or should say that. Oh yeah. I mean, I guess another. Yeah, I mean, a fast way to see that, why that's actually true. This is all based on negative kx equals ma, right? Negative kx, like the spring force, is the net force here. So negative kx equals ma. That's what all my so x and a, look at the equation. They do the same thing, right? When in other words, and this is actually, I'm not even joking about this. What I'm about to write down now starts to get at Lila's question. Like this actually starts to get us into question 9. So maybe I will get into that today just because somebody asked. Like what I'm sort of, my whole system of my body and my tablet and my stylus are not in harmony today. I'm saying this. If we're going to start getting into calculus now, like when I write these things up here, from here on in, these things that I just wrote up in the top right corner, these are fair game for as step 3 GDPs from here on. They might look like out of nowhere to you. I'm not sure what they look like to you. But they are triple equal signs, right? Up here, I'm saying instantaneous velocity, what we call instantaneous velocity in physics, is what mathematicians would call the first derivative of position with respect to time, right? Like now, in principle, again, this is like physics 203 material, but we're going to start getting serious about it now in the formal calculus sense. So when we talk about, and notice there are not bars over the letters. Like it's not v bar, it's just v. Its instantaneous velocity is defined to be first derivative of position with respect to time. And instantaneous acceleration is defined to be second is defined to be the derivative of velocity with respect to time. So if acceleration is the derivative of velocity and velocity is the derivative of position, right? Acceleration is the derivative of position with respect to time. So it's the second derivative of position with respect to time. Again, in theory, this is review, but if we're now at the realm, I think I'm just going to go with Lila on this. Like we may not finish it, but what the heck? I'm just gonna keep talking here on my way into question 9. So at least one person gets their money's worth. So therefore, stop me, Lila or anybody. Like I'm saying now, I believe calculus, what you learn in calculus class about derivatives, just are the mathematical way of thinking of these kinematics terms that we have in physics. They are defined to be those instantaneous rates of change. So when we are a mass on a spring, the force on the mass is the negative kx force. It's accelerating the mass. So I can substitute in, right, second derivative of position with respect to time. I could substitute that in for A and say negative kx equals m d2x over dt squared. How does that help me here in question 8? Well, look. When x goes down, A goes down, right? X and A they're directly proportional to each other. They track each other. When one goes down, not coincidentally, the other one goes down. So then if you take the derivative of both sides, you still have, right? If you do the same thing to both sides of an equation, you don't mess up the equation. So if I take the derivative of both sides, if I write negative k v, that will give me md3x over mdt3, right? I'm just saying, right? I just took the derivative, the first derivative of both sides. So now I'm saying velocity, the velocity at any moment of the mass must be directly proportional to the jerk, not this jerk, the mathematical jerk, right? If the essence of elasticity, the essence of a spring is that you accelerate at a rate that is directly proportional to where you are, like that's like what we're saying. That's what Hooke's law is saying. The farther out you are, the more the spring pulls, the greater rate you accelerate. So if acceleration is directly proportional to position, then derivative of acceleration is directly proportional to derivative of position, otherwise known as velocity. So whatever this does, and whatever this does, this does. And we could keep taking derivatives forever and that would still be true. So what, right? So first of all, I believe that is a rigorous argument. Like I'm saying, this pattern is not just a lucky, like we are correct to believe that the pattern would continue eternally like this. And that means now, I know there's 15 minutes. I'm going to move on to, wow, wait. There's totally interesting things happening in the chat. Wait. Oh, there's a lot of things happening in the chat. Okay, hold on. So I'm about to go to question. So I'm going to move from once I answer the chat. I'm like changing my mind, or I'm whatever. I'm from here. I'm going to start question 9 again because I'd rather do things that people want. And it was a question of secret. We were going to do it eventually anyway. So we're going to start question 9 in a minute. Also, it's just a perfect segue from this. That's why it comes after question 8. But what I'm really trying to conclude right here, what I'm trying to conclude is we have. Okay, very quickly. And then I'm looking at the chat. I'm saying once you accept that this type of motion, this motion that's originally produced by something that looks really simple, F equals negative kx, it's really simple, but it's infinitely rich. It's simple, but it's not easy, this motion. F equals negative kx ultimately means the force, or therefore the acceleration, is directly proportional to position. Now, it is a direct proportionality, but the acceleration is directly proportional to position, not to time, to position. So it ends up producing a motion where it's not just that you go back and forth forever. It's not just that we go there and then come back and go there. It's not just that we go from positives to negatives and back to positives. It's not just that it's not just that we go it's not just that. It's that our speeds also do that. Our speeds go from low to high to low, and then back to high to low again. Like, it's not just where we are that's cycling back and forth. It's how fast we're going that's cycling back and forth. But it's not just that. It's the rate at which we're accelerating that's cycling, oscillating back and forth. Like, we start with high acceleration, then high negative acceleration, then zero acceleration, then higher and higher positive acceleration, then zero. Like, the accelerations are fluctuating back and forth between positive and negative values, just like the velocities are, just like the positions are. But furthermore, the accelerations of the accelerations are, and on and on and on. Necessarily, the minute you put something on a spring, all of its derivatives, all of its rates of change are oscillating in the same fashion as its original position is. That's a new type of motion to us. Nothing in Physics 203 ever did that. Like gravity, you drop something, the acceleration's constant. That's it. Like, it moves and it gets faster and faster, but it gets faster and faster at a rate that is 9.81 meters per second squared. That's it. No other derivatives. This one is oscillation of infinite derivatives. And okay, now to go to the chat. First of all, someone asked very reasonably, I love it. Someone asked, is there a simpler way to do this? Or is that the simplest way? To be honest, yeah, no, I think it's the simplest way. I mean, I'm not saying it is simple. I'm saying we're now starting to get into some hard ideas here. Like, if you find this a little bit wonky, like, I'm with you, but I'm not trying to mess with your mind. Not right now. Like, I don't see maybe if you do, or anybody, I'm not saying this is simple, but yeah, I do think this is the simplest way I could see the situation. Like, I'm basically saying we now have to start thinking about calculus. I think it's a great, I don't know. I mean, oh, wait, I'm reading it specifically. Would there be another way to come by this conclusion? There's definitely other ways. I think they're less simple than this one for me. We could talk about outside of class. I could try to explain this other ways if this is not making sense for you. I could definitely try to explain this other ways. In my experience, the other ways, well, anyway, they might work for you. But if I added them on right now, they would just like clog everybody. So no, I think, but the person who asked, is there other ways? I'm very interested in you. So, it's in public. So yeah, Revo, I'm happy to keep talking about this. I can tell you other ways, but I think they would be a pile-on right now. I don't think they'd make your life better right now. Oh, okay, so but great question, and put that in for points. Then someone else, there's other things. Okay. And I'm going out of order in the chat, but Raymond, great question. Yes, where all this is heading is a graphical way. Yes. Now, am I going to finish the graphical way today? Probably not. Like, yep. But I mean, where this is all heading is graphs known as cosine graphs. What I'm really saying here, I mean, to cut to the chase, if it's helping anybody, Raymond or anybody else, I'm saying if you think about what the thing is doing on meter marks, like where it is at any moment compared to time, ultimately, I'll show you that's going to be a cosine graph. But if you sort of see that, I mean, because it's going back and forth. Oh, actually, I should look. He's in the, right? It's a cosine graph. Where I'm ultimately going to show you is that all of these derivatives, once you see that the first one's a cosine, every one of these derivatives is a moved over cosine, a cosine or a moved over cosine, i.e. a sine. But yeah, we're going to look at this graphically, and this is, I mean, don't get ahead of myself, but if you're like me, Raymond, or anybody else, like, when the first 400 times I ever looked at sines or cosines or trigonometry in math, I was like, wah, wah, wah. Like, I could do it. I'm not, like you guys, I could do what they told me to do. but sines and cosines meant zero to me the first 50 times I dealt with them at all. And sine, I thought they were cool, sort of, but no, they're real. And cosine graphs are real. This is a cosine graph is ultimately where this is going, if that helps at all. That's a great question. Oh, cool, cool. Thank you. Okay. If I could make more, it's so obnoxious that I make everybody show video and then like I like space out and look at the sky anyway. So what? No, but I do see that you're there. I do. Okay. But there's another question in the chat. Hold on. And I know it's 412. Oh, I'm just reading. This is private chat. So I'm just reading. Hold on. Or I mean, direct chat. Oh my God. Yes. Okay, wait. I'm not going to read the person's name, but this is exactly perfect. So someone in direct chat is saying, he or she is just sort of like checking, is this correct? And they say, the acceleration decreases as the mass approaches equilibrium because the restoring force and thus the acceleration is proportional to the displacement from equilibrium, which is getting smaller? Question mark. Yeah. Like, exactly. Like I almost want to just copy and paste that into the public chat because yes, you get it. That's what I'm saying. And now I totally feel like we're having that's great. And yes. Okay. Now we have got 7 minutes for me to try to give Lila a slight degree of at least not, well, I'm not going to call it satisfaction, but maybe not the opposite of devastation. So I'm going to go to question 9. So I will still go back and expand on all those energy things, for good or for bad, whether you want me to or not. But question 9, see now, so question 9 is the heart of this whole matter. Question 9, right? It says at t, equals 1 second. What's x, right? Now that should be the most straightforward physics question in the world. Like in a way, that is all physics come down to. Given the time, what's the space? Like that's all we're ever doing in physics. So. And if this were physics 203, that would be a super straightforward question. We would just like plug it into x equals 1 FAT squared. I mean, we have t, we're looking for x. So we would like plug it into x equals 1 FAT squared plus v naught t or something, and we'd get x. We can't do that. And yes, here, could we plug this in to an xt equation and get the answer? Yes, if we had the correct xt equation for this situation. But right now at this moment, I don't think we do. Like what it said in the homework as hints or whatever is you can't use. All right. So, all right. I'm trying to do step method. We're starting this now. We're not going to finish this today. Although again, if you care, I think the answer that we're going to get is going to be 0.116 meters. But here's step 2. We already have the diagram above, right? This is step 2. What is step 3? GDP. Well, the first thing I'm going to say, I'm going to write, well, the GDP, of course, is exactly what we just did a second ago. The GDP is this and this. I'm leaving out the vector arrows because we already established 2 days ago, like we're going to get rid of the vector arrows. Anyway, it's all in one dimension. So I'm not worried about that right now. We have this, right? In other words, step 3 is this. Right? Like that is step. But note, before I go any further, the big thing of step 3. Oh, and you could also argue, sorry, as long as we're just like I said in the other problem, a step 3 of GDP is also that by A, we always mean this. Like these are all this is all like, these are universal truths about masses on springs. To be even clear, like this and this. These middle 2 statements are true for springs, but the outer 2 statements are true, like no matter what. Hence, one of them is a triple equal sign. But so note, before I go any further into step 4, the key point is that A is changing. A is not a constant. So you can't use constant acceleration equations. Like that is already an important, that's exactly why this is hard, but it's an important truth to recognize. We can't use constant acceleration equations because there is no constant acceleration. So what do? We cry. We take a Prozac. We don't joke about Prozac. We do essentially what we were starting to do in the last problem, where it was good that Ravo asked, like, really, do we really have to deal with that? Like, I may not be comfortable, but it's what we're dealing with now. I'm literally going to say here, negative kx, sorry, equals MD2X squared. I'm doing this. Oh, and let me be clear, like why I'm doing this stuff. I'm starting to solve the problem now. What am I looking for? What we want. Like we want, yeah, it looks like we want X when T equals 1, but really that's just an example. Like the point is, if I had an equation that related X to T, I would plug in 1 for T and get out the X I was looking for. It's not the 1 that is interesting. It's that the interesting thing is, do I have a relationship between X and T for this situation, for a situation where Hooke's law is governing everything. So and the answer is no, I don't have an equation for that yet. That's what I'm really trying to solve for here. Even if I run out of time today, what I'm really looking for, every time I say the answer is 0.116, like for X, like what does that even mean? What I'm looking for is some function of T that spits out X. If I could figure out the relationship between X and T when F equals negative kx, then I would have solved this problem, right? So again, I'm just trying to go as far as I can with this today and set up, and then we'll continue Monday. So what I have is, so far, what I have is I have an equation that has x's and t's in it and nothing else. Like if I just take this thing up here, negative kx equals md2x over dt squared. If I just divide both sides by m, so I can, and rearrange it just so I can isolate. If I could just say second derivative of x with respect to time equals negative k over mx, then what I have there, I don't have an answer yet. I don't have an answer. But what I do have is all the information that I need. I just need a way of rearranging it. In other words, I have, and I know it's 1 minute left, so I'm going to like pause on this for a second. I have a statement where the only variables are x and t. And in fact, where t is the independent variable like it should be, and x is the dependent variable like it should be. That's what I have. And everything else, k and m, are just constants. They're just numbers. So I have some kind of equation here that is one step away. Well, that is contains the package that I'm looking for, but it's a very tightly sealed package. This equation is not my answer yet. I don't know how to plug in a t to this to get out an x. What this equation is known as, and the thing that we're gonna have to solve on Monday, this is known as a differential equation. It doesn't give me x as a function of t. It gives me a derivative of x, in this case, the second derivative of x as a function of t, and relates that back to x itself. Like this is a new thing. That's why you're getting plenty of time to revise the homework and stuff like that to get all the money. This is new. I'm not expecting that you know how to do this from 203 or from math. I'm not expecting that you already know how to do this, but I'm saying it can be done. And it was figured out by people that also didn't know how to do it before they figured out how to do it. So we're going to figure it out together starting Monday. Because the class is just about over now, so we have more to do on this. Like we're not done. I apologize, Lila. But back to Raymond, I'm saying, what the answer, the solution, when I show you how to solve this differential equation, we're going to find out. In fact, I'll even tell you this if it helps. We're going to find out why and how the solution to this is a cosine function. I'm just going to write, sorry, I'm going to write this in case, and you don't have to write this down. You can go, but just if you're looking for satisfaction on this problem or hints or whatever, we're going to find out that the solution to this differential equation looks like this. X equals x naught cosine of square root of k over m times t. Like if you like, that is actually the answer. I'm going to explain on Monday why and how. But it turns out if you put your calculator in radian mode and you put the k of 200 over the m of 0.3, square root them, multiply that by the t of 1 second, take the cosine of the whole thing in radian mode and multiply it by 0.15, that will give you the answer of 0.116 meters. That's how to do it, but that is not an explanation. Like and I don't want to cheat or have you cheat. I'm going to explain Monday where the heck and why I got this cosine thing from, but that's where the ship is heading. I'm glad you actually did a great job of pulling me along. I really appreciate it. We're actually ahead of the game now. Okay, thank you. Yes, okay. Oh, I can use it as well. Oh, sorry. Oh, I missed. Someone gave me permission to put the direct chat in the thing, but I didn't do it in time. So sorry. But yes, got it. I'll do it next time. Okay. Have a nice day. I'll hang around for questions. I'm taking a breath. If there's questions, I'm here. But other than that, have a nice weekend. Have a nice weekend. Um, uh, oh, Tanya, yes. Tanya. Wait, I'm turning off the recording.